In the last section, we learned about constant acceleration for objects that move in a straight line. Well, one of the most common situations where you'll apply constant acceleration, well, nearly that, is that of an object falling under the influence of gravity only. For example, suppose you're standing at the top of a cliff. If you were to drop a stone off the cliff, how fast does it fall? Hopefully you know that it does not fall at constant velocity. The longer it falls, the faster it goes. If air resistance is negligible, then the only force acting on the object is the Earth's gravitational pull. And when that occurs, we say the object is free falling. So free falling is when an object is moving only under the influence of gravity. So no air resistance. Strictly speaking, free fall only occurs in a vacuum. It doesn't matter what mass the object is, they will all fall under the same acceleration due to gravity. I'll show you a demo in class called the feather and coin demo. The constant acceleration of a freely falling body is called the acceleration due to gravity. And at or near the surface of the Earth, its value is 9.8 meters per second squared, and the direction is vertically downwards. We represent that acceleration a in the vertical direction y with a negative 9.8 meters per second squared. Often we represent it, instead of using 9.8 meters per second squared, we represent that value of 9.8 with g. That's a symbol of the acceleration due to gravity. The reason why we have the negative is because it's downwards. When dealing with things in a vertical motion, normally we choose along the positive y-axis to be upwards, and the direction of the acceleration is down, and hence we have a negative sign. On Earth, or near the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared. Other planets have different values. For example, on the Moon, the acceleration due to gravity is 1.62 meters per second squared. It's about 1/6 of the Earth's gravity. Whereas on the surface of the Sun, the acceleration due to gravity is like 274 meters per second squared. On the AP test, the value of g, which is equal to 9.8 meters per second squared, can be rounded to approximately 10 meters per second squared. And we'll be doing this for the multiple choice questions. Remember, on the multiple choice section, you're not allowed to use a calculator, and so it'll be a lot easier to solve those numerical based questions when you can round off g to 10 instead of not using 9.8. When solving free fall problems which are along the y-axis, you may wish to slightly modify our kinematics equations, where I would replace wherever you see the acceleration a, I would replace that with a negative g, where g, by the way, is just simply 9.8 meters per second squared. So you can see in here we have replaced the a with a negative g, and you'll have a negative in front of some of the terms. Furthermore, since you're dealing with things that are along the y-axis up and down, you may also wish to replace all of the x's with y. So maybe change that x sub 0 to y sub 0, and you could change that here and here in your expressions. It's not necessary, but it's helpful, just because later on we're going to be dealing with two-dimensional motion, and we'll be using these equations for the vertical motion anyhow. Before we get started into some problem solving, I think it might be helpful to address a few common misconceptions with free fall. First, let's consider not just a ball that is dropped. Let's take a look at a ball that is thrown straight up in the air. First, when does the ball actually have this acceleration of 9.8 meters per second squared downwards? Should we consider the toss itself when the ball is in the hand of the person who's throwing the ball, or when the ball eventually hits the ground below? Is it accelerating at this same rate? Well, hopefully you know that the ball has an acceleration due to gravity of 9.8 approximately downwards only when the ball is moving through the air. We do not consider the toss of the ball or when it makes impact with the ground. Remember that an object is under free fall when the only force acting on it is the force of gravity. If the ball is still being thrown upwards with that extra force from the hand pushing it upwards, or the ground hitting it when it makes impact with the ground, then there are other forces acting on it, and the acceleration is not 9.8 because there are other forces acting on it. And we'll get into this reasoning later on when we talk about forces. So let's visualize the motion of the ball by drawing the ball's motion in the air. And we're just going to pick a couple of locations of the ball. I'm just going to label this as 0, 1, 2, 3, and 4, these locations. By the way, technically the ball is thrown straight up and straight back down, but I've drawn my picture slightly horizontal so we can see all the vectors that we're going to be drawing in a minute. First, let's take a look at this position 0, and let's label that initial velocity vector v sub 0 upwards as it leaves the thrower's hand. Now, the ball slows down as it rises. Therefore, the velocity v1 at a later point in time has a smaller magnitude than the initial velocity when it was thrown from the hand. By the way, what is the direction of the acceleration as you look from position 0 and 1? Hopefully you've guessed it. It is downwards in this direction. Here we go, another one. I'll just label that as a G, and it both has the same magnitude of 9.8. It's in the opposite direction of the velocity, which means it's slowing down. At the top of the path, what's the velocity? Hopefully you've guessed it, v2 will be 0 at the very top of the path. But what about the acceleration? Is there no acceleration at position 2? Take a moment and think about this. Is the acceleration 0? No, it isn't. Many people make this error. This is a common misconception that people will think that the acceleration due to gravity is 0 because the velocity is 0. Actually, the acceleration is still downwards, 9.8. It's still in the air. The ball wouldn't be able to turn around if it had 0 acceleration. If it just basically get up to the top, it had 0 acceleration, it wouldn't be able to come back down. So remember, it's still accelerating at the top. Even though the velocity is 0, it's turning around. It's changing direction. The velocity is changing because it's a vector. So what happens when it comes back down? What's the speed at point 3? Or what's the velocity at this position 3? Well, the velocity at 3 is exactly the same magnitude, same size as this arrow, except it's in the opposite direction that it was at point 1. What about at point 4? The velocity at point 4 is exactly the same velocity as the initial velocity v sub 0. They're both at the same height. The only difference is it's in the opposite direction that it was initially thrown upwards. So basically, if you were to throw the ball up, say with, 20 meters per second of a velocity, and if you were to put your hand below it and leave it the same spot you threw it, it's going to hit your hand exactly at the same speed. It'll just be in the opposite direction. Also, the acceleration is still downwards at a constant value of 9.8 meters per second squared. Notice that as when the ball was thrown upwards, the acceleration g was in the opposite direction of the velocity, and hence that's why it was slowing down. But on the way down from 3 and 4, the acceleration is in the same direction as the velocity, and hence the ball is speeding up. And one other last misconception that I alluded to earlier, the ball, when it hits the ground, we know the ball will eventually stop. But at that point in time, the ball is no longer in the air. And once the ground is starting to apply a force on the ball, then you can no longer say that it is a constant acceleration of 9.8 downwards. So this acceleration due to gravity 9.8 is only when the ball is in the air. Okay? And remember, at the top of the path, it still has acceleration. It's 9.8 meters per second squared down. Okay, I hope you are ready to solve some problems.